welcome to the lectures on fundamentals of MIMO wireless communications. We were in the previous lecture looking at the different ways of calculating error probability, and we have also taken the general criteria of diversity, where we said there are m number of parallel transmissions. These parallel transmissions could be in time domain, or could be in frequency domain, or could be in space domain, and we had arrived at the general expression of error probability, where we had shown that the error expression could be in general given in this form, as it is clear over here, where the m in the denominator came because there was m parallel branches, and the transmit power was divided among the m parallel branches. And we have also said there is this exponent raised to the power of m, because typically in CISO the error probability is inversely proportional to SNR, but here it is increased to the order of m, which is bringing in the diversity gain. In this expression we have discussed the effect, we have discussed the expression which has d mean squared, and in the beginning we had equated this to gamma b. Here we said the d mean squared is equal to 4 EB. So in this way we could do the translation. At this point it is also important to note that in some cases we might have another way of writing the expression. That means in some places, in some references, you might find that probability of error is given as approximation of PE any bar. That I'll explain all the things. Q function of square root of d mean squared by 2, and rather more accurately times eta, where eta, or we could also write this as gamma, where gamma is the SNR. So if you look at this expression, this is the number of nearest neighbors and d min is the separation distance between nearest constellation point, and gamma is the SNR, signal to noise ratio. In case of AWGN, this SNR would be ES by N naught. In some cases ES is taken to be 1. In that case you have d mean squared by 2. In case of fading channel, so this is AWGN. In case of fading channel, it should be ES by N naught times HF squared, which is the Frobenius norm of H squared, that is the channel squared. In case of CISO, this is simply ES, it is simply ES by N naught times H squared. This is what it is, and in some cases, in some references, you will find PE error probability is given as alpha m q function of square root of beta m times gamma. This gamma is the same as SNR, and beta m is a coefficient, alpha m is a coefficient. Here we have been using this expression in earlier cases, but this m, this particular m, is the constellation order, constellation size. That means if it is pulse amplitude modulation and there are 4 levels, so m is equal to 4 in this case. If it is QAM, so for this case m is equal to 4, for this case m is equal to 16. So like that, this m is dependent upon the constellation size and not the spatial m, and we might be confused with these expressions. So there is equivalence, there is of course equivalence in these expressions, and clearly alpha m is same as any bar. So that's how these coefficients are usually derived, and this beta m naturally is the same as d mean squared by 2. So if we use these translations, then these expressions turn out to be the same, and the error probability expressions work out as the same. So there is no more problem with them. So you might find this in different places, and for details on these you could refer to many different books. One of them would be Wireless Communications by Andrea Goldsmith, and the expressions that will be following mainly would be with this. So on and off we'll be giving the translation with respect to alpha m and beta m and show their equivalence. So as of now I'll carry on and show you how they are the same exactly when we take just pure diversity case. So for the diversity scenario, we said that the received signal in the ith branch or the ith instant of time or ith frequency or ith received signal is root over Es by m, assuming there are m transmissions, and it is done in such a way that the total energy remains the same, plus this is the channel coefficient for the ith copy of the signal. S is the signal. Ni, we have described Ni in the previous discussion. So, and we wanted to combine the signal in such a way that the signal to noise ratio at the receiver is maximized. So, we will use maximal ratio combining, where we say Z is equal to sum over I equals to m. Mind it, this m that we will be using here is different than this alpha m and beta m. So, this alpha m beta m would be modulation, but this m is different. So, wherever suffix of alpha or beta is there, it is related to the constellation and not to the spatial dimension. So, carrying forward, we would like to combine it as hi squared y I. So, this would lead to root over Es over m times, of course, there is a summation I equals 1 to m. I again say this is the spatial dimension, mod hi squared s plus hi conjugate, of course, sum I equals 1 to m Ni. This is the received component, and when we calculate the signal to noise ratio, so the gamma in this particular case would be the square of this term. So, we are going to get Es over m, and when I take the square at the power of this term, we will be getting E of Ni conjugate, and we have already described previously how Ni would be. These will be zero mean circular symmetric complex Gaussian. So, and they are independent of each other, that we have already mentioned in our previous discussions. So, we are going to get n naught in the denominator because of this, and we will be getting in the numerator sum over mod hi squared I equals 1 to m. This will happen because the square of this divided by the square of this, you will be going to be left with this particular term, and this you could write it as, if I take Es by n naught as gamma bar, which is Es by n naught divided by m, because there are m transmissions each having 1 by m of the power, times mod hi squared I equals 1 to m. So, this is the same as we had before, and then as we deviate or as we start comparing the two expressions, so clearly Pe is by 1 Ni bar q of square root of eta d mean squared by 2. This is what we discussed in the previous lecture, and the other one is alpha m q of square root of beta m times eta or gamma, sorry. So, we would use eta for this particular expression, which is gamma over here. So, that is using the Chernoff bound, this is less than or equal to Ni bar e to the power of minus will eta d mean squared by 4, 2 and another 2 because of Chernoff bound, and here is less than or equal to alpha m e to the power of minus beta m eta by 2, and this is equal to Ni bar e to the power of minus, if you see this expression, it is gamma bar by 4 m gamma bar, I have already taken this, times mod hi squared I equals 1 to m, and this one is equal to alpha m e to the power of minus beta m, but it's all the same basically, gamma bar sum over mod hi squared I equals 1 to m. And the next step would be to calculate Pe bar, that is expected value of probability of error. So, using the technique which we have done before, this would turn out to be Ne bar times product of 1 by I equals to 1 to m 1 plus gamma bar, sorry, here there is a d mean squared, we had missed there, 4 m d mean squared, and here also what you get is alpha m pi I equals 1 to m, this is the spatial dimension, 1 by 1 plus beta m by 2 gamma bar, of course beta m by m, right. So there is straightforward symmetry in these expressions, or it could be written as 1 by 1 plus gamma bar by 4m d mean squared raised to the power of m, and here alpha m 1 plus beta m by 2 gamma bar by m raised to the power of m, and for gamma bar greater and greater than 1 we had any bar gamma bar d mean squared by 4m raised to the power of minus m, and here also alpha m beta m by 2 gamma bar by m to the power of minus m. So again everything is the same, so the equivalence here also, it is d mean squared by 2 is equal to beta m. So with this equivalence everything holds true. So we'll be using either of these two expressions as and when applicable. So there is no reason for confusion amongst this expression. They are all equivalent in their own places. So with this we'd like to carry on with our discussion on diversity. So as we move forward with our expression of diversity, we'd like to explain something about the diversity gain. So the order of diversity gain is typically represented by this exponent of error probability. This is very, very important. So if we'd like to compare, let's say this is the probability of error axis and this is the SNR axis, signal to noise ratio in dB. Let's say this is the SNR axis in dB and this is the error probability. So if without any diversity, let's say this is the error probability curve. With diversity, what happens, as we clearly see in these expressions here, that the error probability is now raised to the power of m. So that means clearly there's the slope of this is order of m. So when there is diversity gain, this particular curve becomes like this. So there is an increase in slope in the error probability expression. This is the diversity gain. So what it leads to is, if I take a particular SNR value, at that SNR the error probability was at some point here. Now because of diversity, the error probability has come down to this point. So there is significant gain in diversity, in error probability, because of this diversity gain, and this kind of gain because of which there is increase in slope of the error probability curve is usually described as diversity gain. It's basically increase in magnitude of the slope of this, can be described in terms of increase in magnitude of the slope of the probability of error curve. Along at this particular point, it is also important that we describe another kind of gain which is associated with these, is known as the coding gain. In coding gain, what we would experience is that the error probability curve shifts laterally to the left direction. There is a lateral shift in the error probability curve, and this is usually noted as the coding gain. Sometimes array gain is also reflected in this kind of performance. So this coding gain usually comes from smart ways of encoding the transmitted signal, which could be error correction codes or any other kind of code. So there is a left shift in the error correction in the probability of error curve. So the two distinct kind of gains can be observed in the error probability expression versus SNR, and we can identify whether there is a diversity gain or whether there is a coding gain. So if we would look at the probability of error expression, the average probability of error expression, in such an average probability of error expression, we could say that the expression looks like as if there is some constant and there is a gamma c, a coefficient, times, let's say, gamma bar, which is the average error expression, average SNR raised to the power of m. Now this constant, we can't do anything but this particular exponent is basically giving us the diversity order or the diversity gain that is available, and this particular coefficient is indicating of the coding gain. So, this is how these two gains can be understood when looking at the probability of error expression. And if we take a look at this particular curve, it would be evident that this is also equals to C gamma bar raised to the power of minus m. So, if I take the log of probability of error, because this is in the log axis, right. So, we could take it in the log domain. This would be some logarithm of C, some constant term, plus minus m times log of gamma C plus log of gamma bar. So, clearly what we can see is that there is this left shift because of this, and this is causing the additional increase in probability of error expression. So, clearly you can also understand it in these terms. So, essentially diversity gain, as we are seeing, as SNR increases, the gain due to diversity is significantly higher, whereas the array gain is almost the same in all range of SNR. So, the curve essentially from here just simply shifts to the left. So, it translates, whereas here the curve changes the slope, and as SNR increases, the gain that is achieved is much more than compared to in the condition where the SNR is less, and that is also evident here because the SNR is raised to the power of m. So, higher SNR, there is higher order, and the gains are even more. This is something important which we would like to remember when we are understanding diversity gain or coding gain. So, after this we can see that when we look at spatial diversity, we said you could obtain it at the receiver or you could obtain it at the transmitter, or you could obtain it on the both side. On the receiver side, we have seen there is selection combining, there is maximal ratio combining. We have seen the PDF of SNR in both the cases. We have seen how to calculate error probability in case of MRC. For selection combining, we have given you the expression. To get the exact numbers, one has to do numerical technique. So, now it is time that since we have looked at how diversity can be taken advantage of at the receiver, we would like to see how diversity can be taken advantage at the transmitter. So, when we go to the transmitter, again there are two techniques. One is with channel state information at the transmitter, and another is without channel state information at the transmitter. We will take a look at the with channel state information as well as without channel state information. And finally, you could obtain diversity gains by using both transmitter and receiver at the same time. We will also have a look at that slowly in the few lectures to come. So, when we look at the transmitter diversity, so if I am looking at diversity at the transmitter, and that too we will be focusing at channel state information known at the TX. We will use TX at the transmitter. In short, we can say the channel known at the transmitter. Okay, and we will begin with the case. We can always consider the case where there are multiple antennas at the transmitter and there is single antenna at the receiver. So, this is the case which we will consider. So, this is basically the MISO, multiple input single output scenario. So, we will remain with our assumptions of the channel. So, in this case we will assume that the channel vector is given by H1, H2 up to HMT. This is the convention that we have used. In case of CMO, that is single input multiple output, this was a column instead of a row. Now, So basically we have this particular configuration, and we'll assume that there is some weights associated with each antenna. There is a weight associated with each antenna. Same signal is being transmitted. So the received signal, which is combined, we had written the expression earlier, is given as root over ES by MT. There are MT number of transmit antennas, H times W times S. S is single, this is a vector, this is a vector, and clearly this will be a column vector, this is a row vector, and this W is basically the weight of the matrix, weight of the channel coefficient, weight of the antennas that are to be used. So this is MT cross 1, and this is 1 cross MT, and S is of course a scalar, and we have to choose that the Frobenius norm of W is equal to MT. Right, we have already divided this by MT for each branch, and will with this together it will ensure that there is ES power. So there is no change of total transmit power in this particular case. So, and we will further choose the W vector to be root over MT H Hermitian divided by root of Frobenius norm of H. So what we are essentially doing, if you would look at it carefully, H Hermitian, so that means H is a row vector, H Hermitian is the conjugate, and it is the column vector. So the row vector of H and this is the W getting multiplied with each other, we can predict that almost H11 squared plus H22 squared, H2 squared plus dot 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 up to HMT squared is going to appear over here, and that will be the Frobenius norm squared, and there will be this MT and this MT will cancel out each other. So we are going to get something like the receive MRC. So what we have over here is, in other words, you can say you have transmit MRC, this transmit maximal ratio combining. This is done in order to maximize the received SNR. So with this thing, when we write the expression of the received signal, that is Y, what we get is Y is equal to root over ES upon MT, of course H Hermitian square root of HF squared, that is W, this is W, this is the W that we have here, plus there is of course this noise sample that is present. So now in receive MRC we had channel coefficients getting multiplied here as well, but here it's not the story, but overall the performance would turn out to be the same as we would see. So we are getting square root of, sorry, there is a root, this factor we have missed out, root over MT. So MT goes out, you are going to have ES. This is basically Frobenius norm of H squared time divided by HF square root times S plus N. So essentially what we have is root over ES square root of HF squared S plus N. This is the received signal. Now clearly from this we can write the expression of SNR, eta or gamma, whatever we write it as ES by N naught, this square divided by the power of this times HF squared. So if you would see this expression, it is again the same expression as that of MRC expression. So naturally we are going to expect the error probability to be similar to that of MRC expression, right? So when we write the probability of error expression was approximately given as NE bar Q function of square root of eta d mean squared by 2. So that is NE bar Q function of square root of, for this we could write as gamma bar HF squared. So basically we are going to have gamma bar d mean squared by 2 times hf squared. Rest of it would follow any bar. This is less than or equal to e to the power of minus gamma bar d mean squared by 4 times hf squared. This 4 because this whole squared divided by 2, the argument of this square divided by 2, so 2 times 2 is 4. So we have this. Now this would naturally lead to is equal to any bar pi I equals 1 to, here it is mt 1 by 1 plus gamma bar d mean squared by 4. Right. So what is different than the pure diversity case? There was an m over here because there were like m separate branches, but in this case the m is gone because we are doing this kind of combining. It's because particularly because of the w that we have chosen in this case, so that helps a lot. And so this would lead to approximately any bar times, when gamma bar is much bigger than 1, gamma bar d mean squared by 4 raised to the power of minus mt. So when mt equals to m, this is the same as the other one. When d mean squared by 2 equals to beta m, and this is equal to alpha, so you have alpha m gamma bar beta m by 2 minus of m or mt. So this is again the same expression as that of MRC. Now here what we should note is when we are calculating this expression eta, so eta or gamma is given as gamma bar times hf squared. So if I have to take this, I would write it as gamma sigma. The expected value of gamma sigma bar is gamma bar times the expected value of this. The expected value of this is h11 squared plus h1 squared plus h2 squared up to hmt squared, and e of h1 squared is equal to e of h2 squared, and so on. So and e of h1 squared, so basically if you look at this, this is sum over hi squared, I equals 1 to mt, and there is an expectation. So with independent assumption, you have e of hi squared and a summation, and each of these is equal to 1, and this summation is equal to 1 to mt. So together you're going to have mt. So basically this times mt. So what you get is that there is an average increase in SNR, as well as there is this diversity gain of order mt even in this scheme. So what we can say is, in this form of transmit diversity, when channel is known at the transmitter, we have the transmit MRC scheme, and what it boils down to is the performance is same as that of the receive MRC. So if you are doing transmit MRC with full knowledge of channel at the transmitter, you would get the same error probability expression as that of receive MRC, and the performance is identical to that of receive MRC. We stop this lecture at this point. Thank you.